Okay. Okay. Hi, so I'm Sarah Dean Rasmussen. I'm chair for the last session we have today. I've been very grateful to be a co-organizer for this conference. And we've had some amazing speakers come. And today we'll have our last Panorama speaker, our youngest, but already a giant in the field, Maggie Miller at the University of Texas at Austin. And she'll talk about knotted surfaces.
Yeah, okay, thanks for having me. I was writing this, I looked at the list of talks for today, and I was like, these are like kind of more about knots. And then I realized I just misremembered. It's supposed to be called knots and surfaces, my bad. So I lean more on the knot side after that. But I'm still going to focus on problems that have to do with the intersection between knots and surfaces. And I'm sort of leaning away from concordance, especially the structure of the concordance group. Obviously, that is a very important topic. But I think we've heard a little bit about that this week, and it kind of seemed more natural in some of the other sections. And also I put a panorama, so. Okay, so I'm going to give you a timeline, about 100 years. It's actually pretty hard to narrow down what I think the most influential results in the study of knots and surfaces are. This was like, okay, small selection. So I'm going to flip through to sort of give you an idea of what I thought the major themes were. I started at 1925 because that is when Artin wrote, not the Artin you're thinking of, Artin wrote the paper introducing sort of the first interesting knotted surfaces and other dimension, so Artin spun knots. And in these early papers, we see mostly just really basic constructions, you know? Like, okay, it's Alexander polynomial 1928. It's not like I'm going to tell a grad student now to go read that paper, right? But I think we can all agree that that's one of the most influential results in this area of mathematics. Okay, and so as we keep going forward, the 50s and 60s sort of see the advent of a lot of the big motivational questions that we still study today, and an increasing number of interesting examples as we develop more techniques. As we get into the 1970s, we start to be able to at least try to classify families, although we're not very good at it even still. In the 80s, as we've heard in previous days, we start to see the study of smooth or exotic behavior, and that includes in the context of surfaces and four manifolds. We see exotic surfaces in many different contexts. In the 90s, and I think on that last slide, I forgot to say Friedman. Ooh, skip over that. But we also have these diagrammatic theories, in some ways easier, I would say, than the study of exotic behavior, but still really not formalized until the 90s or even early 2000s. We have several different diagrammatic theories in the study of surfaces. It's like a different group of people who study exotic behavior versus surfaces from a diagrammatic point of view. I saw there was a poster about quandles at the poster session, and I was like, yeah, you probably really care about this like Rosman moves if you're doing that point of view. And then with knot floor or Khovanov homology, the existence of cobordism maps has really influenced a lot of recent study of surfaces, I think. And now there's still a big emphasis on exotic behavior, but that is not all that exists in the current modern study of surfaces. Like, certainly it's important, but there are other interesting topics as well. So that was a lot. I just flashed on the screen. I didn't count, but I think that was like 20 papers. That was more than 20 papers. But so I'm clearly not going to tell you what each one of those was about, because that would be awful. So instead, I sort of went through and tried to figure out what were the main themes of the results that I thought were the most influential in the area. And for the most part, all of the results that I just flashed up on the screen, I think fall in the categories of classifying families, which again, we're bad at in this dimension, by which I mean 4. Knots bounding in higher dimension, that of course includes classical knots, questions of sliceness and ribbonness, but that's still something that is interesting in higher dimensions. I'm going to try to tell you something about surfaces bounding into 5. Unknotting questions, which can mean a lot of different things, but that has always been a motivation in the study of knot theory. And then exotic behavior, which it's not the only thing, but it's a very important aspect in this field. Okay, so my plan for the talk, because I don't want to go through a list with 20 papers and just tell you, here's my favorite, because actually my favorite paper is not on that list. I think that I'm going to tell you a bunch of motivational problems some of which a lot of you already know, and it might be more like a status update of here's something interesting to think about, and some of which you might not have previously thought of before. And they're mostly from the K3 problem list, and so I'll give you like historical references and also what's happening right now with some modern things. Okay, so I want to start off with a problem that I know we all know. I know we all know this problem. So ribbon knots, we've seen this. This is the obligatory, like I can't just say you all know what a ribbon knot is, that's not polite. So I've made a slide. Okay, so we do all know, I think, that a knot K is sliced if it bounds a disk in the 4-ball, and then you have to be annoying and say, is it smooth or locally flat, and I guess they're different. And then a knot is ribbon if it bounds a disk in the 4-ball. And for ribbon, we always need a smooth disk, unless you want to put the word homotopy in there, and I don't. So it's going to be a smooth disk, because for a ribbon, I want there to be a radial height function that restricts to a Morse function on the disk. So it has to be smooth for that to even make sense, and I want to have no local maxima. So I always draw this picture when I'm giving a talk or like teaching, because this is how I like to think of the schematic. The arbitrary slice disk is bad on the left, and the arbitrary ribbon disk is good on the right. Okay, so of course the motivational question is every slice not ribbon? And this is a really old question at this point. I think people usually cite Fox's A Quick Trip in Knot Theory, but actually I think it's not in there. I think it's some open problems in knot theory, but they both came out at like the same time. Also, I might have just totally mixed those up, don't correct me. This is in Fox's work, and of course it's the question, is every slice not ribbon? So just given the existence of a bad slice disk, does that mean there's some other good ribbon disk? Which can be a subtle question. I'm certainly not claiming that every slice disk can be isotoped to become ribbon. That's not true. It's just, could I find some somehow unrelated ribbon disk? We know that it's true for some families of knots, 2-bridge knots, most 3-stranded pretzels. I really liked, at the start of the conference on Monday, Josh Green, from what he said, I can firmly consider these to be prehistorical. So there's not that much modern progress towards proving the slice ribbon conjecture after 2013, I'm sorry. There are some sporadic families that we know that it's true, but I think for the most part, that's because, let's be honest, the slice ribbon conjecture can't be true, right? That'd be crazy. Why would that be true? Just from having a slice disk, why should there be a ribbon disk? And 4D, nothing good can happen, and that would be good. So I doubt that this is true. And then the problem is, well, how would you possibly disprove something like the slice ribbon conjecture, right? And so I thought that I would start off by telling you my favorite potential obstruction to the slice ribbon conjecture, which if any of you have seen me give a talk before, I bet you've seen me talk about this, because I say this theorem more than I think any other theorem. This is a paper by Casson and Gordon, 1980s. They studied a connection between ribbon and fiberedness of knots. I'll put a picture in a second, because I'm sure we said fibered, but I kind of don't remember. But if a knot happens to be fibered as well as ribbon, then the knot comes with a monodromy, which is a surface automorphism. And the fact that it's ribbon tells us that actually that automorphism has to extend over a handle body, by which I mean a solid of genus G. So here's the picture. A fibered knot means that its complement fibers over the circle, in which case the fibers are then surfaces bounded by the knot, Seifert surfaces. So the knot complement then, as a bundle over the circle, it's fiber, cross I, and with the ends glued together. But the ends aren't glued in a trivial way, like the identity map that would be surface cross S1, that doesn't even have the right homology to be a knot complement. Instead, we have to glue the ends with an automorphism of that surface, and that's called the monodromy. It's technically defined in a surface with boundary, but it's the identity on the boundary. So it makes sense to cap off and think of it as an automorphism of a closed surface, and then you can question whether it could extend over a handle body. So that's that picture on the bottom left. So I want to emphasize that this is a real restriction. Like, certainly the average surface map does not extend over any handle body. That'd be crazy. Knot monodromies are special maps, but still, for the most part, fibered knot monodromies do not extend over handle bodies. This is a real, serious obstruction. Okay. And so it's not so obvious from this how I would decide if a monodromy extends. Other people can. I'm not very good at it. But there are some papers that give examples. So, well, why is that the next one? Oh, I forgot to tell you, okay. So if I want to point out that if you have a knot that's sliced and fibered, but the monodromy doesn't extend, that means it's not ribbon, so that's why it's the sliced ribbon would be false. Okay, yeah, I put that on the slide. So one example in which we just know that this theorem applies is from work of Miyazaki, who I think he was Cameron Gordon's postdoc, so this is about 10 years after the paper, and so he was working on this at UT. And so he showed that that previous statement applies automatically to any cable of a fibered knot with irreducible Alexander polynomial. So if you have a fibered knot, the cables are still fibered. And I can understand, in the case of a cable, what the monodromy is in terms of the initial monodromy of the knot. And he sort of boiled down to, in particular, I have this very simple condition of irreducible Alexander polynomial, that's enough to obstruct that extension. So this is, I think, a really nice result because it's easy to apply and I don't have to think that hard. And it's easy to think of interesting fibered knots with irreducible Alexander polynomial. So here's another related result. Kawauchi, 2009. He showed that if I have a knot, which is strongly negative amphichiral, I put this because one of the lightning talks today is going to be about a generalization of this result. Getting rid of that word strongly. But he showed that this condition implies that a knot actually bounds a disk, maybe not into the actual four-ball, but into a rational homology four-ball. And so strongly negative amphichiral is a name we use for a certain kind of rigid knot symmetry. It's telling us that I can take something like the figure-8 knot. So the figure-8 knot is equal to its mirror reverse, that's a symmetry. But you can see in this left picture, I've drawn it in a very symmetric way. Right? So those left and right points are connecting through the point at infinity. And the figure-8 knot has a symmetry, which I guess I'm not going to fully explain because I don't know what's in the lightning talk, and I kind of felt guilty about it. But it's some sort of rigid symmetry of that picture where I rotate and reflect. And so if I cable the figure-8 knot, it stays fibered. And if I take an even cable, it actually becomes algebraically sliced. And it's also still rationally sliced. That follows from the fact that the figure-8 knot was rationally sliced. So this particular knot here on the right, where those endpoints are glued together in pairs, is a fibered knot, which I know is not ribbon, but it is rationally and algebraically sliced. So it's very difficult to prove that it is not sliced because most of our slice obstructions fail for these families of knots. You have to think pretty hard. Okay. Unfortunately, some people did think hard. And so a few years ago, Daikong Malloy-Park Stoffergen proved that this particular knot is not smoothly sliced. The word smooth in there, it could be topologically sliced. That would actually be super interesting. They're using techniques that come from, I forgot to check what the adjective was, but I feel like it's involative floor or something. But it's very important that it is a smooth, in the smooth category. Their paper is not so specific to literally just the 2-1 cable of the figure-8. They apply to other certain 2-1 cables. I'm not going to say like a general condition. And then some of these authors, Kang Park and then also Taniguchi, extended that last year to include just actually any even cable of the figure-8. So you can't just cable the figure-8 and disprove the slice ribbon, which is quite annoying because that's like clearly the best fibered knot other than the trefoil and the unknot. So the 2-in-1 cable of the figure-8 knot does not violate the slice ribbon conjecture. But again, all of these papers, while perhaps not totally specific to the figure-8, are specific somehow to something about the figure-8, some property of its floor homology, not floor homology. So here's the smallest knot that the argument doesn't apply. This is a cable. I didn't draw the original knot. It's a cable of a 10 crossing knot. The important thing about this 10 crossing knot is it has R from variant 0, which means fundamentally the arguments, I think, of these 3 papers cannot apply, at least immediately. So this knot, 1017, is fibered. So this cable is still fibered, and I know from Miyazaki that it is not ribbon. But this knot is also, because of 1017 symmetry, rationally sliced and algebraically sliced. So maybe it's slice. I don't know. So, of course, if you were able to prove this knot is slice, that would really change your week, I think. That would be a very good result. If you were able to prove that this knot isn't slice, that would be a very good result. If you were able to prove that this knot is slice, that would change your week, I think. That would be a very good result. If you were able to prove that this knot isn't slice, that would change your week, I think. That would be a very good result. If you were able to prove that this knot isn't slice, that would change your week, I think. That would be a very good result. If you were able to prove that this knot isn't slice, that would change your week, I think. That would be a very good result. If you were able to prove that this knot isn't slice, that would change your week, I think. That would be a very good result. If you were able to prove that this knot isn't slice, that would change your week, I think. That would be a very good result. If you were able to prove that this knot isn't slice, that would change your week, I think. That would be a very good result. If you were able to prove that this knot isn't slice, that would change your week, I think. That would be still be like pretty good. I should have checked this too, but I'm pretty sure that first paper is like an inventiones or something. So I don't know, if you could do a few more knots, it's like maybe like what, inventiones GT, you know? Is that, I don't know, is that controversial? I'm sorry, there's a bunch of editors in here. Okay. This is on tape. Oh my God, okay. Dave isn't here. Okay. So I think this is what I wanted to tell you about the slice ribbon. That's my little update. I think this knot is the smallest knot for which there is a good reason to consider it as a potential counterexample. I'm not claiming that, oh, we know the slice ribbon conjecture is true for all knots less than this number of crossings, because I don't think that that's true. And also, I don't know the crossing number of this knot. There's no reason to think this is minimal or something. But I cannot think of or find an example in the literature of a better knot to consider. Okay, so I'm just putting that out there. So that's something interesting. Oh, okay. So I want to tell you something else about ribbon disks while we're on the topic, but I think I'm going to move on from slice ribbon because I don't know how to do it. Oh, no, I didn't. I forgot. I had one more update. I've had one more update about slice ribbon. This is like the most exciting thing that's happened this month. So here's an old strategy for trying to disprove the slice ribbon conjecture. So you might have seen these before. One way of constructing ribbon knots is through an operation called symmetric union. I think if you study especially knot theory, I'm pretty sure there was a poster about symmetric union yesterday. If you study knot theory, I'm sure you care about symmetric union. Symmetric union is where you take a knot and its mirror, and you attach them, not exactly as a connected sum, but also you add them together more times, like as according to this diagram. So there's some number of half twists in each of those boxes. So if I just had 0 for both of those, this would be connected sum. So maybe I have something like this. So this is I had 2 5 torus knots on either side, but one is a mirror, and then I've symmetric unioned them. This is relevant because this always gives me a ribbon knot. And at first I tried to draw the ribbon disk, and I was like, I think that's only helpful if you already know what the ribbon disk is. My bad. But it's just, you take these horizontal lines that connect the tangle to like the corresponding point in the other tangle, and they'll together foliate an immersed disk in dimension 3, and it has ribbon immersions. When you push it into B4, it can become embedded as a ribbon disk. So these are ribbon knots. And another K3 problem was asking, is every ribbon knot a symmetric union? And that would be very interesting from the point of view of the slice ribbon conjecture, because it turns the ribbon condition into a very three-dimensional condition. In principle, it seems like this is something that we could obstruct. So if we knew that this was true, then I could actually try to prove a knot isn't ribbon using this, right? Unfortunately, actually, we can obstruct this, and you can even do it for ribbon knots. So at the start of June, Michel Boileau and Kitano and Nozaki proved that this particular ribbon knot is not a symmetric union. And I have an AIM square with Michel, and he posted this like the week before, and I was like, oh my God, I thought we were doing homework right now. And this is such a good paper. And it's actually like a very, in some ways, elementary proof. So you might recognize his name if you do knot theory. Michel Boileau has probably thought about the meridional rank conjecture more than like anyone else. He has a ton of papers about meridional rank conjecture in different contexts. And so this knot, first of all, it's ribbon, because if I apply ribbon moves here, like saddles, and split off, I get 4 unknots on the left, and then a stevedore on the right, which is ribbon, so that's why it's a ribbon knot. But then they give a group theoretic argument. It's all just fundamental group. Based on the double-branched cover of this knot. If it were a symmetric union, there'd be a surjection from the double-branched cover, pi1, to the pi1 of the double-branched cover of like the quotient under the symmetry. And so it's just like an algebraic argument why that's not possible. And so it is kind of interesting. This is like a side note. This is not really relevant to slice ribbon, I think. But it's very important that this knot has a very complicated double-branched cover. And so they actually ask, if you have a knot with determinant 1, maybe this Kirby problem is still true for it. So that's a side note, but I thought that paper was very interesting, so I wanted to advertise it. Okay, so now we're done with slice ribbon, I'm pretty sure. Sick. So even when we know a knot is ribbon, something we could ask is, what is the structure of the set of ribbon disks? How many ribbon disks does it bound would be a good start. So let's restrict to the easiest case. is every ribbon disk bounded by the unknot isotopic to the standard ribbon disk, which is just the one that comes from S3, like the unknot bounds a disk, and you push it into B4 a little bit. That's the standard ribbon disk. It's, to me, crazy that we don't know the answer to this question. I can rewrite this as, like, what is pi 0 of the space of, like, these kinds of embeddings, disks that are ribbon with unknotted boundary. And I think it's crazy because this is, I think, literally the simplest family of surfaces in 4 manifolds. Like, I'm going to put it out there that disks are easier than spheres because disks are contractible. I don't know. I'm in the 4-ball, which is clearly the best 4 manifold, and I have unknotted boundary, which is clearly the best boundary. But I still don't even know how many disks are in this space. Okay. So here's an example of a ribbon disk bounded by the unknot. So on the left, I have a bunch of minima, 3. And as I go from left to right, I have these index 1 critical points that appear with respect to height. And at the right, which is supposed to be the top, I have an unknot. I don't know why I put this picture here. You don't have to, I'm sorry. But it looks complicated because in the middle, wait, do I know how to, no. Oh, I don't like that. Okay, never mind. In the middle cross-section, you can see that it's like a non-trivial link. There's a stevedore component, so it's like, that looks bad. That looks like a complicated ribbon disk, right? But it's actually really hard to generate interesting examples in the first place. So in fact, I would claim that in some sense, obviously this disk is standard. I don't want to say what obvious means. But if I exchange the heights of the 2 index 1 critical points, it kind of all just like falls apart. Don't look at that hard. But so many knots do have ribbon disks that we can distinguish from each other. So pi 1, by which I mean maybe the inclusion of S3 minus the knot to B4 minus the disk, is a way of distinguishing disks from each other. I put Zeeman as a reference just to indicate that this is something that we've known for a very long time, although maybe Zeeman's result was something to do with isotopy rel boundary, but still. You can also distinguish disks with more modern techniques. Knot-floor homology cobordism maps, Khovanov cobordism maps. This Juhász-Zemke result, I think, is the first example of knot-floor distinguishing disks. That's not an exotica result. It's just a way of doing, like, it's a technique. And then later, we do know that there's also exotica results using knot-floor homology. And then this Hayden-Sundberg set of disks are actually exotic. They're topologically, but not smoothly isotopic. So pi 1 can't do that, but these modern cobordism maps can. Unfortunately, any technique like this is going to be trivial in the case of boundary equals the unknot. So that's cheating. Because I guess if you've knotted boundary, maybe spheres are better. So I don't know how to answer that question. Advertisement. Okay, moving on. Sliceness and other 4 manifolds. Okay, because I was like, I don't want to talk about concordance, and I don't, Irving told me don't say you don't like anything. I don't want to talk about concordance, but so I thought I would talk about sliceness in other 4 manifolds. I think this is an interesting problem. I think there's a lot of people thinking about different aspects of this right now. I put a Kirby problem that I like. Does every knot bound a smooth disk into, in particular, how about 2 CP2? Punctured, so they have boundary. How about K3? I know that Andras has thought about these problems quite a bit. So let's say that a knot is sliced into a 4 manifold. If it bounds a smooth disk into that 4 manifold minus a ball, so that it makes sense, I have boundary S3, okay? So I'm gonna use like this cursive S to indicate the set of all slice knots. So the set of all slice knots in S4, that's just slice in the usual sense, right? Because that means K bounds a disk into B4, okay? So if you're sliced, like regular, then you gotta be sliced everywhere else too, because you could just use your slice disk, the regular one from B4, you can just put it into any 4 manifold you want. But sliceness in other 4 manifolds is interesting. So this Yasuhara result, 1990s, showed that sliceness in CP2 is different from sliceness in S4 in a non-trivial way. There are knots that become sliced into CP2, like the trefoil, that aren't sliced into S4. But it's not like every knot becomes sliced into CP2. And I think yesterday in Ali's talk, I could be misremembering, but I think it was Ali, mentioned the Norman trick, that there are also examples of four manifolds like CP2 sum CP2 bar or S2 cross S2, where sliceness just trivializes everything slice. I thought I would show you the Norman trick. I don't know if everybody has seen it. It's a very useful, I think, trick that comes up all the time in the study of surfaces. I always forget to call it the Norman trick. But the trick is, in both of these four manifolds, I have two very interesting spheres. So I put one in pink, and that's a sphere like S2 cross point, if I'm in S2 cross S2, or maybe it's CP1 connects in CP1 bar, but it's a sphere who has trivial normal bundle. And then I also have another sphere, and they intersect once, and it's just another sphere. So that could be point cross S2, so it's like the two factors in S2 cross S2, or it could be CP1. And so the reason that this is interesting, if I take a knot in the boundary, like it bounds an immersed disk, because I could just like unknot the knot and like trace out some homotopy to the unknot, so I get this immersed disk up at the top. What I'll do is I'm going to connect it to a copy of this green sphere. And I put these like squiggles on the right to indicate, I don't know the green sphere's normal bundle. Like if I take a parallel copy of the green sphere, it probably intersects itself. One of my students in the audience is colorblind, and like, I hope this is cool, Nathan. But, okay. So now I have this immersed disk still, but I have a tool, which is I have this pink sphere that intersects my disk once, and the pink sphere is trivial normal bundle. So for every self-intersection, I'm just going to get rid of it by replacing it with a copy of that sphere. And the pink sphere is trivial normal bundle, so I didn't like make intersections, like pink sphere is still cool, it only intersects my disk once. I can repeat this process. Okay, so that's the Norman trick, just FYI. It's a pretty good trick. But this is very specific to this setting. I don't usually expect to have a bunch of spheres floating around my manifold. So some open problems include finding any four manifold other than CP2 or CP2 bar where sliceness is interesting, by which I mean it's not literally everything, but it's also more than just S4. We actually don't know any other example, for sure, other than CP2. It's somewhat related to something else that Ali mentioned yesterday, of the ability to obstruct sliceness into certain homology classes. CP2 has very simple homology, it's rank 1. If I take a four manifold with a bigger rank, bigger Betty number, there's going to be a bunch of primitive homology classes, and I'm not going to be able to easily obstruct sliceness into those homology classes, so that's a problem. And that leads to this other Kirby problem. If I give you a smooth, simply connected manifold with B2 bigger than 1, is it true that just every knot is slice? Like maybe I can't do the Norman trick, but maybe there's just some other reason. And there's some motivation to think that the answer is yes, because it is topologically. Every knot is topologically sliced if I have big Betty number, which is crazy. But this Kaspersky, Powell, Ray, Teichner, really locally flat category, not a smooth construction. So I don't even know how I feel about this question. I don't know how you would obstruct the sliceness though because of the homology situation. We're in Budapest, so here's the most interesting recent result, sort of in this vein. So Marco and Stefan Mihalovic, who I don't think is here, but was also a student of Andras, proved a few years ago that as long as my unknotting number isn't too big, which to be clear, less than 22, that's like every knot fathomable, right? I mean, other than like a connected sum of 22 trefoils. Wait, do we know? We don't know that, right? We don't know that has unknotting. Okay, yeah, okay, I don't know. As long as I have unknotting number less than 22, then my knot is sliced into K3. And you might even be able to guess the proof, because it is somewhat the Norman trick. The key thing here is this structural result of Finishin Michalkin, 90s. Using the fact that K3 is an elliptic fibration, they find inside of K3 a plumbing of 22 spheres. So I put this graph on the left that's supposed to indicate like each vertex is a sphere, and there's an edge to indicate spheres intersect once, and then otherwise they don't intersect. So like there's a schematic of that same thing on the right? And I don't know what the normal bundles, well actually in this context, actually I do know what the normal bundles are, and I feel like it's all -2, but I forgot to check. +2, -2. But I'm just not going to put framings on those. And so the point is, if I have an immersed disk, as long as it has less than 22 intersections, I can repeat the same argument from before. Like, okay, I add it to like one of the spheres, and now all of a sudden, like I'm intersecting a bunch of the other spheres once, and each one of those intersections, I can get rid of it at the cost of like using up a parallel copy of one of the other two spheres in this plumbing. And if I keep going, like I'll use up more and more spheres. I can only get rid of so many, namely 21, but I can eventually get an embedded disk. So that's like a pretty clever argument. Okay, but well, I don't think that there's plumbings of arbitrarily high numbers of spheres into K3 or to whatever other four-manifold you're interested in studying. So it's not clear how to use this technique to generalize to study arbitrary knots. So I still don't know how to answer sliceness into K3. Okay. Moving on again. I know I'm going like all over the place, but you said panorama. So sliceness, one dimension higher, which is the good one. So here is my favorite theorem, which, okay, I said my favorite paper is not on the list, which is true. This paper was on the list, but it's my favorite theorem, but it's not my favorite paper because it's in French. So this is Curver proved that every two-knot is slice, in the sense that any two-sphere in S4, you can say smooth or locally flat, bounds a ball into B5, which is smooth or locally flat, whichever category you want to work in. Which is amazing, because again, I know I said nothing good is true in 4D, and I still feel like that's true, but okay, like we got this one, right? Like concordance is so hard in dimension 3, and like this is the only time where it's like, we got them, you know? So this is one of my favorite theorems. If I were teaching a mini course or a class, I would definitely do the proof and not lie that much. I think I'm going to tell you why it's true, but I'm going to lie a lot. So that the proof is that I have my two-sphere in S4, this is how you draw S4, and I like to think of it as being at the top, and then B5 is everything below it. So here's my sphere, and in S4, my sphere bounds some three-manifold. That's just a homological condition. S4 has no H2. So my two-sphere bounds a three-manifold, orientable, and I push that a little bit into B5, and it's probably not a ball, right? But I know that I could turn it into a ball if I were allowed to do Dane surgery to Y. So I just take whatever knot inside of Y that I want, and I'm in B5, which is simply connected, and this knot bounds a disk. I'm not even worried about the disk intersecting itself, because B5 is so high dimensional, disks are always embedded generically. And so I'm just going to thicken that disk, think of it as a four-dimensional two-handle, and I'll do surgery. I'll delete a neighborhood of the knot from my three-manifold and replace it with the boundary, the rest of the boundary of this two-handle. And so that does integral Dane surgery to this knot. And that was somewhat of a lie, because I didn't say how to control the framings. But if you noticed that, then you know how I control the framings. And if you didn't notice that, then you don't care. So the question that is most pressing about this topic is that every link, is it true that every link of two spheres, so more than one two-sphere at a time, is slice in S4? It's well known, by which I mean just the proof literally works the same. If the link is a boundary link, then it's slice. So boundary links, if you haven't seen this before, this is, I think, a very common topic in the study of knot theory. A boundary link means that my components simultaneously bound disjointly. So in the context of surfaces, it would be they're bounding disjoint solids. I drew below this like a classical link. It looks like a Whitehead link, but I Whitehead doubled one of the components. And see, like they bound disjoint surfaces at the same time. And then I have things that aren't boundary links, which is they don't bound disjointly. So things like the Whitehead link on the bottom right, kind of famously not a boundary link. Of course, the two components each bound, but those surfaces are forced to intersect each other. It's kind of hard for me to draw a surface link in S4, but it's not a boundary link. That's really stretching the imagination. But you know, surfaces are bad. So if my link happens to be a boundary link, and I have like maybe two spheres, and they bound disjoint three-manifolds, I can just literally do Curver's proof, sort of like parallel side by side on the two three-manifolds, and surgery them both to be B3. The issue is that if I started off here in the If I started off here in the boundary with a connected three-manifold, like they intersect each other, they're not disjoint, no amount of Dane surgery can fix that. So I really need them to be disjoint. So unfortunately, that can't be a strategy towards answering this question, 1980s, Cochrane, not every link of S2s is a boundary link. He gave an algebraic obstruction to being a boundary link. This is a paper, I think, that has just like so many citations. There's some interesting constructions also in this paper and some related papers he wrote at the time, interesting knots and links of two spheres. So, okay, you can't do that. And I wanted to also point out in the 90s, so about 10 years later, Stong wrote a paper giving a potential algebraic obstruction to sliceness of a link. I kind of meant to have a slide so that you wouldn't have to look at all of this text at one time, but I forgot to put a line break here, so like, sorry. But so Stong gave an invariant of concordance of spheres in four manifolds, and it's valued in first homology of the four manifold that it's in. So if you have a sphere in S4, there is no first homology, so there's no obstruction, which makes sense because all two spheres are sliced, consistent. But if I have two spheres, then I could think of one as being in the complement of the other. So like delete sigma 2, now I have some first homology, then maybe the invariant for sigma 1 could be non-trivial in there. So there's some open question of whether or not this Stong invariant is actually realizable in this setting. And that's really the only potential obstruction to link sliceness, higher dimension, that I am familiar with. So if you're trying to prove links are not slice, I don't know how to do it unless this works, and this probably doesn't work. Okay, so sliceness of links, my favorite Kirby problem. I was talking about it with Danny this week, and he said he's thought about it. I'm sure Danny's thought about it way more than I have, obviously, but he says he's thought about it a lot. And I was telling him, every time I see Rob Schneiderman, he tells me, like, he's been thinking about it a lot, and so I don't think I could ever catch up, but very interesting open problem. I do want to point out that the two-sphere case is kind of special. So Nathan Sanukian, this is not the full statement of the theorem he proved, and this is my actual favorite paper, but he proved in particular that the Curvaire theorem holds for positive genus surfaces too. So every genus G surface in S4 is slice in the sense of not bounding a ball, but bounding a handle body, so a solid of genus G. So all oriented surfaces are slice. But links of positive genus surfaces are like typically not slice, but for trivial reasons. So I drew this picture here on the right of what I would call spun hop flink. It's like if I took a hop flink cross S1, fit inside of S4, I get two tori. And those two tori, like just sort of like, again, obviously can't be slice because each one represents a non-trivial homology class in the complement of the other surface. So like I can't even have T1 bound in the complement of T2. And then as I'm going into B5, like they can't simultaneously bound. So that's like a very coarse obstruction to sliceness, which can't hold for two spheres. For two spheres, if I look at the complement in S4, Alexander duality, there's no H1. There's no, oh my God, I put H1, that's so embarrassing. I meant H2, my bad. I do know that tori are two-dimensional. Ooh. But there are more subtle invariants, analogs of Milner's invariants in dimension 4. In particular, there's this great paper, Adu Mehan Yasuhara, 2021, and I think they have some other work extending Milner's invariants in dimension 4. If you're familiar with Milner invariants, as pretty cool, not topological category sliceness obstructions. Okay, so that was sliceness. I don't know what slide is going to be next, but I'm pretty sure it's not sliceness anymore. Oh my God, it is. It is true that if you add any structure to the three balls, you can say something like, I don't want to say obstruct sliceness, but you can obstruct simple sliceness. So again, Sanukian, such a cool guy, different paper, he proved that there are lots of two-nuts who, even though they're slice, the slice balls have to have some positive genus cross-sections with respect to radial height. So that's my picture on the right. Like it has a genus 2 cross-section. And then Remy Baum, who's my student who's here, proved last year, and this is not the full statement either, but in particular, there are symmetric two-knots, and they're sliced because they're all sliced, but they can't be symmetrically sliced. So if you extend the particular kind of symmetry over B5, you can't find a three-ball that respects that symmetry. So this is somehow suggestive, I think, that links might not be sliced, because it's kind of like an extra structure, right? If I'm like, okay, can you find a 3-ball that's disjoint from another 3-ball? That seems like less, I don't know, that seems less likely than finding like a symmetry extending thing to me. So I think that links aren't slice. Please don't be about sliceness. Yes, nice. Okay, so everybody's favorite, exotica, I think. So I'm going to focus on S4 because other 4 manifolds are, I don't want to say other 4 manifolds are hard because S4 is famously hard, but other 4 manifolds are scary. So in particular, here's a K3 problem. Is there a pair of oriented surfaces in S4 specifically that are topologically but not smoothly equivalent? I'm saying equivalent instead of isotopic because, I mean, isotopic would also be fine, but then we have to discuss like the diffeomorphism group of S4. I kind of don't know. So I'm just going to say equivalent. And I'm also saying S4 because we know, I think we've already discussed, that there are lots of examples of pairs of so-called exotic surfaces in other 4 manifolds. But in S4 specifically, we still don't know the answer to this. And it's not clear what techniques could obstruct surfaces from being smoothly equivalent when they are topologically equivalent. I underlined oriented. Because we've already talked about some of these this week, but there are lots of non-orientable examples, and they've existed in the literature for quite some time. We've had exotic connected sums of 10 RP2s inside of S4 since the 80s, finishing Craig-Viro. Finishin improved this down to connect sum of 6 RP2s, and then just a few years ago, Miyazawa, that was like a crazy paper, right? But he had this family of just single RP2s in S4 that are exotic. So non-orientable examples, like you can go down as small as you want. We know that there are exotic pairs. I don't know if everybody, well, I know that not everybody is familiar with the obstruction in these papers. I don't know how many people have read these. Maybe the Miyazawa one, I think a lot of people have looked at in the last few years. This original paper, Finishing Craig-Viro, they have these surfaces that they know are not smoothly equivalent by looking at the double branched covers. So one of them, the double branched cover is like CP, again, I'm missing a bar. I realize that CP2 sum 9 CP2 is 10 CP2, but it's supposed to be CP2 sum 9 CP2 bar. And that's homomorphic to a Dolgotchev surface, like all of the Dolgotchev surfaces. And so they realized some family of Dolgotchev surfaces as double-branched covers of S4, and also the standard one is a double-branched cover of S4. And the branch loci in S4 can't be smoothly equivalent to each other because their double-branched covers are not diffeomorphic to each other. So that's the smooth part of the proof of this result. And the Finishin result is similar. It's the same argument, except instead of a Dolgotchev surface, he's using some exotic CP2, some 5 CP2 bars. Something interesting about the Miyazawa paper is he's still using the double-branched cover, but in his context, the double-branched covers are both CP2. He's distinguishing these RP2s, and they're literally just both CP2, diffeomorphic to CP2. And so he is doing something a little bit more subtle of not just distinguishing the manifolds, he's actually distinguishing the involutions, which are like the covering actions on these double-branched covers. So this is this real Seiberg-Witten theory. That's like a very cool technique. But in any case, it always boils down to the double-branched cover. So if you were trying to study orientable examples, one difficulty is that the double-branched cover of S4 with an orientable branch locus always has signature 0. So it's not CP2 or CP2 connect some 9 CP2 bar. But we do have signature 0 exotic manifolds. So a few years ago, Akhmedov Park Sokhali made some exotic connected sums of S2 cross S2s. I think even before this, Akhmedov Park had connected sums of S2 cross S2s, but I forget what the number, it was like a big number. It was like 100 something, right? And then I should have put that still, but I couldn't remember how many it was. And then with Sumera, they got down to 27. And then Inoch Biker and Hamada, a few years after that, improved the S2 cross S2 number down to 11, exotic 11 S2 cross S2s. And they also have exotic smooth structures on connect sums of like same number of CP2 and CP2 bar, but a lot of each, like at least 9 of each. So those are signature 0 manifolds. And so in particular, an actual connected sum of S2 cross S2s, like not exotic, just literal, is a double branched cover of S4, where the branch locus is an orientable surface. The genus is equal to the number of summands in the S2 cross S2. So one question is, like, can you realize any of these, especially the S2, S2 ones, as double branched covers over S4, these exotic guys? So these ones don't come with sort of a natural involution like those Bogachev surfaces. You got to find a good involution and then hope that when you take the quotient you get S4. But I don't have a reason why you can't do that. And if you could, then the branch loci could not be diffeomorphic or smoothly equivalent to the standard orientable surface of that genus in S4. So they might be an exotic pair. So that would be very interesting, but I don't actually understand these constructions, so I'm not going to try to prove that they have like involutions, but okay. So here's a related problem. I think this should have been the first problem in some sense on these slides because it's the most famous, but it's also like the hardest for me to talk about. So this is the Kirby problem list 4.29, which I'll tell you, the knotted surfaces section, when I was writing this before, I thought it was not sand surfaces, when it was just knotted surfaces. I went through the Kirby problem list, and there's 17 knotted surface problems, and 4 of them are good, and this is the first one in the section. This is like, I think by far the longest write-up in that section. I think so many people have thought about this problem, and I have very little interesting new to say about it, but I will tell you about the problem, which is if I have a surface in S4, and for now let's say it's a two-sphere, and the complement is homotopy equivalent to S1, which is the same thing as saying the fundamental group is Z. There's a reason that I've written it like this. Must the surface be smoothly unknotted, by which I mean bound to ball? Okay, so if I have an actual unknotted two-sphere, one that bounds a ball inside of S4, and I take its complement, it is homotopy equivalent to a circle. That's something that's true. The fundamental group is Z. So this is like, can homotopy type of the complement detect the unknot? Okay, that's the question. And it's kind of a coincidence in this dimension that for the unknot, pi1 actually determines the homotopy type. So I wrote it like this because in higher dimensions, actually this unknotting problem, the answer is yes. Even smoothly. If I give you a smooth codimension 2 sphere in at least dimension 5 ambiently, and I tell you, oh, the complement is homotopy equivalent to S1, then that implies that my sphere is smoothly unknotted. So that's J. Levine in dimension greater than 5, Shanison in dimension equal to 5. I didn't put these onto my timelines at the beginning because they are specifically high dimension, but I felt bad about it. And then in the topological category, actually the answer is also yes. So Friedman, I put CFQ because everybody cites Friedman-Quinn. I'm a little bit, I think it's this one. I think it's 1983. He proved that every two-sphere with a complement homotopy equivalent to S1 locally flatly is unknotted, so it bounds a locally flat 3-ball. Okay, so we mostly understand the answer to this question, except in specifically dimension 4 in the smooth category. And there's 2 fundamental problems here. I think the obvious one is like, how would you possibly prove that a two-sphere is not smoothly standard? I don't know. And then even if, like, let's say you tell me you have some like awesome new invariant and you can like prove that two spheres aren't smoothly equivalent, and then like you come to me because you know I study knotted surfaces and you're like, can you like give me a sphere that like has the right homotopy type, but you can't just immediately tell it's the unknot? And I would be like, no, how would I possibly do that? It's really hard to generate examples. I would try pretty hard if you had a good invariant, but I don't know how to immediately do it. This problem isn't only about spheres, though. I could also ask about positive genus surfaces. And then I could ask this question about the smooth and topological category. And so I want to know if they're unknotted, which just like in the slice setting before, it means that does my surface bound the simplest possible thing, which would be a genus G handle body. So does the I feel like I've written the wrong homotopy type. This is like, I'm going to be honest that I finished my slides at about 1 a.m. last night, but I think that I only want to say that the fundamental group should be Z. Yeah, okay. I can't ignore that. There we go, okay. But is it true that it bounds a handle body? And so in the topological category, for high genus, yes. For genus 1 and genus 2, though, we actually don't know. That's weird. And then that was Conway Powell, just only a few years ago. This is new. And then for genus equal to 1, there's a paper around the same time, Juhasz and Powell gave just several interesting families of examples where they either proved that they were topologically unknotted, or there's an interesting family which they kind of advertised, which kind of existed in the literature before, but then like this is like a really good source to learn about it. I'll tell you in a second. And then smoothly, like literally nothing. I have no idea what to say about this problem. Having genus does not seem to make it easier to obstruct the surfaces from being smoothly equivalent. I guess it maybe makes it easier to make examples, but we still have no techniques. And then there's the non-orientable version of this question. So now if I tell you of a non-orientable surface and the fundamental group of its complement is cyclic, in this case, cyclic can't mean Z. It has to mean Z mod 2. Again, that's Alexander duality. Do I know that the surface topologically is unknotted? And so the word topological has to be here now, because I just told you all about finishing Craig-Vero and Miyazawa. Like, we know that there are lots of surfaces in S4 that are non-orientable, which are, in those examples, they're all topologically unknotted, but they're not smoothly unknotted, so this has to be topological. And I've also deleted my parenthetical where I said what it means to be unknotted, because you might notice that RP2 doesn't bound anything. So I can't just tell you RP2 is unknotted if it bounds like something, right? Unless I'm really careful about what that thing is. Usually we define unknotted diagrammatically. Again, I think it's funny to just like kind of put that up there. Here's 2 different pictures of unknotted RP2s, just like cross sections left to right. So unknotted just means a connected sum of these things. And that is meaningless if you haven't already thought about it before. But the point is that unknotted is just like some standard example that we know really well. So the question is, does a very simple fundamental group tell us that the surface has to be standard, even topologically? And we don't know. We know a lot. For just RP2, we've known that to be true for 40 years, Lawson. For connected sums of small numbers of RP2s, it's true that they're topologically unknotted. That's Conway, Orson, Powell, and then Marpinkovich. And for even large numbers of RP2s, as long as the Euler number is not too big or too small, we know that actually they have to be topologically unknotted. And that's that Conway, Orson, Powell again. It's easier to say in which cases this conjecture is unknown. So we don't know the unknotting problem to be true for even non-orientable surfaces when we have a connected sum of a large number of RP2s inside of S4. And the normal Euler number is plus or minus 2n, which is just, that's like the biggest that it can be. That's not obvious. That's like usually called the Whitney-Massey theorem. But these are examples of these are examples of non-orientable surfaces in S4 whose double-branched covers are definite manifolds. That's the equivalent condition. So kind of an interesting topological problem. Okay, so I did want to tell you this interesting family. So this is in the Juhasz Powell paper. This is like an explicit family of surfaces that you could think about if you're interested. So I have a torus inside of S4. The case that I'm going to think about is like, how do I make the surface as easy to deal with as possible? I'm going to say it has only one minimum and only one maximum, which is just the smallest number that it could possibly have. So my torus literally, in some sense, looks like this on the left, combinatorially. So I have a minimum, I have a maximum, and then just to get the right Euler characteristic, I got to have 2 index 1 critical points. Okay? Is that condition enough to prove that T is smoothly unknotted? No idea. I actually really thought about this problem specifically in graduate school for like a little bit too long, and I have nothing interesting to say about it. And is it topologically unknotted? We actually don't know. I'm sure that Andras would have something interesting to say about that, but they didn't know these examples in this paper, although they discussed it. It's a very interesting family. And because it's genus 1, Conway-Powell doesn't apply. And this problem is specifically in the old K2 list as 430. Now it's just incorporated into the unknotting problem in K3. Okay, so I've successfully advertised a lot of what I think are kind of big picture questions in this area. I tried not to just do literally the problems that I'm thinking about. You might have noticed that I successfully didn't tell you literally anything that I did. Good. Here's your homework. I have this slice knot again. That's the most concrete one. Oh, sorry. I don't know if it's slice. Ooh. But I have this knot here, which if you could decide if that's slice or not, that'd be awesome. Can you make ribbon disks with unknotted boundary? Because I don't know how to do it. How do you construct interesting Z surfaces, let alone try to distinguish them from each other? Those S2 cross S2s, the exotic ones, can you realize them as double-branched covers? Over S4, or I guess over anything would probably be kind of interesting. And then this Kerver-Milner invariant of Stong, I'm going to be honest, that's the most opaque question here. Don't ask me to tell you what the Kerver-Milner invariant is, because I'm going to give you a reference that's not fun to read. But I can't believe, can you guys wait? I got down to like within my, okay, anyway, so thank you.
Any questions for Maggie? Anyone? Yeah.
The room is too big for the microphone thing.
Non-maths question. Did you draw that?
Oh, yeah, it's just notability.
Okay. I thought you deserved credit if you did.
Sorry, could you repeat again? So the Kerver-Milner thing, I won't ask you what I don't know, but I won't ask you. But so if you could find a sphere like that, like why does that, is that a link that's not slice?
Yeah, if the S1 cross B3 is S4 minus the unknotted sphere. So if you found a two-sphere inside of S1 cross B3 with non-zero Kerver-Milner invariant, like let's call the sphere like S, then the two-component link that's S along with the unknot that you deleted to get S1 cross B3, that two-component link would not be slice. Yeah, does that make sense? She said, yeah, okay.
Any others?
Is there an example we should think about with where we do know the Kerver-Milner invariant is non-trivial?
An example where we know that it's what? Where it's
non-zero.
Oh, there are examples where it is non-zero. It's just they're in ambient form manifolds where we have more H2. So in fact, inside of, you can make an example in S1 cross B3 blown up twice. One CP2 and one CP2 bar. You can find two spheres that as a pair have non-trivial Kerver-Milner invariant. But I don't know how to do those constructions when there's no second homology, because you're kind of using the Norman trick, actually, to make things be embedded.
All right, well, let's thank the speaker again. And we have 4 lightning talks today instead of 3. Is that still true? Yeah, so try to come back at 10:25 instead of 10:30 today. So it's John Baldwin from Boston College. He'll talk to us about ribbon concordance and fibered predecessors.
Okay. So I'd like to start by thanking the organizers for putting all this together and inviting me. It's an honor to speak at this non-celebration for Zoltan and Andras, 2 people who have had an important impact on my life. Zoltan, after all, was my postdoctoral mentor, and Andras taught me a lot of Hungarian curse words. showed me that middle-aged men could be really good at soccer, which is inspiring now because I'm at this point older than when I learned this lesson from Andras. No, but he also gave us Gonfin Stipschitz, of course, as well as the lesser-known Osbachi Stipschitz, which is also great. And shout out to Barack Osbachi. I wish I could say that this conference had been a lot of fun for me, but I got sick immediately on arrival, so I was sort of holed up in my room, and I watched most of the talks online. But the silver lining of that is that the cameramen get these really good shots of the audience. And so the YouTube live stream is like constantly interspersed with like close-up, high-definition shots of familiar faces belonging to people, in some cases, that I hadn't seen for years. Some of whom I met for the first time when I was here for the first time in 2004 at that legendary summer school and conference. And that was the summer after my first year in grad school. I was still riding high off of my first year course in modern geometry taught by John Morgan, which is the course that convinced me that I should be a person who studies geometry and topology instead of something crazy like number theory. And I just started reading Gonfin Stipschitz, and I was toting that all around Budapest. And I brought it to all the lectures, and when I got horribly lost in a lecture, I would open the book and read it. I went to Peter and Zoltan's mini courses, of course, and I remember thinking, wow, Zoltan is such a good lecturer. The other distinct memory I have is there's a lot of chatter about open books, and for reasons I can't really explain or justify, I found that terminology so silly and childish that I kind of vowed that I would stay far away from open books. Of course, you know, I wrote my thesis on open books in Hegardt floor homology, and they've been central players in a lot of the work I've done since. And this talk is no exception to that. So without further ado, let me tell you something about ribbon concordance and fibered predecessors. So everything I'll talk about today will be joint with Stephen Sivak and with Sivak and Jonathan Hansenman. Okay, so a smooth concordance from a knot J to a knot K is called ribbon if the projection to the interval has no local maxima when restricted to the concordance itself. So the picture I drew on the first page is meant to illustrate that. This is a cylinder from the unknot to the connected sum of the trefoil in its mirror, and, well, this cylinder has index 0 and index 1 critical points, no index 2, no local maxima. Okay? And so we use this less than or equal terminology to indicate that J is ribbon concordant to K. And sometimes we'll also want to keep track of the ribbon concordance itself. So we'll do that in the subscript. So this is a generalization of what it means to be a ribbon knot, what it means to bound a ribbon disk. If you have a ribbon disk, you can puncture it, and you have now a ribbon concordance from the unknot to K. So I should say that this was introduced by Gordon in the late 70s. And the sliced ribbon conjecture is the statement that a knot is sliced if and only if it's ribbon, which is the same as saying that the unknot is smoothly concordant to K if and only if it's ribbon concordant to K. Okay? But unlike smooth concordance, ribbon concordance is not a symmetric relation. It's reflexive and transitive, but not symmetric. And there are a few ways to see this. One convenient way is to think about the exterior of a ribbon concordance. So if C is a ribbon concordance from J to K, then let's just remove a neighborhood of C from S3 times the interval. And you can think about this as some cobordism with corners from the exterior of the knot J to the exterior of the knot K. And this is what's called a ribbon cobordism in the terminology of Daimi, Lidman, Velovic, and Wang. And all that means is that it can be formed just from one handles and two handles, four-dimensional one handles, four-dimensional two handles. In other words, the concordance complement, you can get it by taking the complement of J thickening it, and adding 4-dimensional 1 handles and 2 handles. So these correspond to the 0 and 1 index critical points of the concordance. This is a nice exercise if you haven't seen it. Okay. So one of the things that Gordon proved in his paper from '78, I believe, is that if J is ribbon concordant to K, then the knot group of J injects into the fundamental group of the concordance complement, and the knot group of K surjects onto the fundamental group of the concordance complement. And one of these is very easy to see from what I just said. So namely, if we can form EC, the exterior of C, from the exterior of J by adding 1 and 2 handles, then you can think about this backwards. You can also form the exterior of the concordance from the exterior of K by adding 2 handles and 3 handles. So when you add 2 handles and 3 handles, you're not adding any generators to pi 1, you're just adding relations. And so that's why, oh, here we go, you get this surjection. The other direction is significantly harder, and I won't talk about it here. But in particular, there's this corollary that if a knot is ribbon concordant to the unknot, then it must equal the unknot. And just that follows immediately from this surjectivity fact, right? If K here is the unknot, then this is Z, and so this is abelian. Now this knot group injects into an abelian group, it's also got to be Z, and so this has to be the unknot as well. So this shows that the ribbon concordance is not a symmetric relation. Okay, so that was the late 70s when Gordon introduced all of this. Much more recently, I think around 2019, Ian Zemke showed that actually a ribbon concordance induces an injection in knot flow homology. So if J is ribbon concordant to K, then the knot flow homology of J injects into that of K in each Alexander grading I. Here we go. So I here is the Alexander grading. And this is really powerful when paired with a theorem of Ojvath and Szabo from around 2004, which describes how knot flow homology detects the genus of the knot. So the genus of the knot is just the maximum Alexander grading in which this knot flow homology group is non-zero. Okay? So let's see what those two things together imply. So yeah, what they imply, an immediate corollary is that if J is ribbon concordant to K, then the genus of J is less than or equal to the genus of K. So genus is monotonic under ribbon concordance. And Zemke used this to prove, in particular, that genus is superadditive under band sum of knots. And the idea there is that if you have a band sum of several knots, there's a ribbon concordance to it from the connected sum of the same knots. And genus is additive under connected sum, and so by this inequality you get the result. So that was known, the superadditivity of genus under band sum was known previously in the case you have a band sum of 2 knots. That's an older result of Gabai. And so Zemke's result proved it for arbitrary band sums. Okay, so in this paper, Gordon made several conjectures. I'm going to tell you 3 of them here. So the first is that ribbon concordance is a partial order. And I've already said that ribbon concordance is a transitive and reflexive relation. That's easy to see. And so what's needed to know that it's partial order is that if J is ribbon concordant to K and K is ribbon concordant to J, then J is equal to K. And that was resolved by Ian Nagel in 2022, so it's a pretty recent result. And that's the reason for the notation less than or equal. The second conjecture that Gordon made is that the partial order is well-founded. So I didn't really know what that meant, but what it means in concrete terms is that you can't have an infinitely descending chain of ribbon concordant knots. Or maybe more precisely, if you have an infinite sequence like this, then eventually these knots have to stabilize. They're all the same after some point. And then the third conjecture that I'd like to at least mention is that volume is monotonic under ribbon concordance. And if the knots are hyperbolic, then you should interpret volume to mean simplicial volume. Okay, so the result that motivated the work in this talk is, or the conjecture that motivated the work I'll talk about today is the second one. All right, so that's what I'll focus on for today. All right, so you can't have an infinitely descending chain of ribbon concordant knots. So when I was thinking about this last summer, I realized that there's a much simpler thing you could ask, which is just given a knot, let's say K1, can it have infinitely many ribbon predecessors to begin with, whether or not they fit into a chain like this? And so that's the conjecture that Stephen and I first started to investigate. For each knot K, there are only finitely many J that are ribbon concordant to K. And the result that I'd like to tell you about is a partial result in this direction. So for each K, we can show that there are only finitely many fibered J that are ribbon concordant to K. All right. Any questions? Okay. So I should mention, actually, that Ian Nagel and Chi Ren, just shortly after we posted this paper, came up with another proof of a slightly weaker result, where they also assumed that K is fibered. But what's interesting about their proof is that they can also, using their method, show that volume is monotonic under ribbon concordance if you assume that both J and K are fibered. So it addresses this third conjecture of Gordon that I mentioned. Okay. So one corollary of our theorem is that the conjecture at the top actually holds for all fibered K. If you assume that K is fibered, then it has only finitely many ribbon predecessors, period. And the simple reason for that is this result of Silver and Koshlikova, which says that if K is fibered and J is ribbon concordant to K, then J also has to be fibered. And so then J satisfies the hypothesis here in our theorem. Okay? So I want to spend the rest of the time trying to give you an idea about how we proved this theorem with Jonathan Hanselman. All right, so here's the theorem. And, so, why is fibered important? So people have talked about this before, but just recall that, what it means for a knot to be fibered, loosely, is that you can describe the exterior of the knot as the mapping torus of some surface homeomorphism. So it's some surface bundle over the circle, right? So you take the surface, compact surface boundary, times an interval, and glue points on one end with points on the other end by some homeomorphism of the surface that we call the monodromy of the fibration, or of the knot. And so the idea behind the proof of the theorem is to try to constrain the monodromy of any fibered ribbon predecessor of K. And if we can constrain the monodromy, then we can try to understand from that the knot complement. And we know that J is determined by its knot complement by Gordon and Lukey. Okay? So that's the rough goal, and I'll make this more concrete and precise in a little bit. But we're going to do this by analyzing the monodromy of potential ribbon fibered predecessors of K. Okay, so here's the proof sketch. So let's fix our knot. And let's suppose that J is ribbon concordant to K by some concordance C. Suppose that J is fibered, and for simplicity at first, let's suppose that J is hyperbolic. Okay. So the fact that it's hyperbolic means that its monodromy has a certain special form. It's freely isotopic to what's called a pseudo-Nassau homeomorphism of the surface. And furthermore, we also know, for example, from Zemke's theorem, we can constrain the topology of this fiber surface S. So the genus of S is the same as the genus of J, which is less than or equal to the genus of K. So there are only finitely many possible topological types of S. All right. So what does it mean for a surface map to be a pseudo-Nassau? I mean, if you know the Nielsen-Thurston classification, then it says that a surface homeomorphism is either freely isotopic to one that's periodic or reducible or pseudo-Nassau. But pseudo-Nassau maps can be characterized as well as those which fix a nice pair of foliations on the surface. So a map being pseudo-Nassau means that it fixes a pair of transverse measured singular foliations on the surface. And they're measured foliations, and what the map does, well, it fixes them the leaves setwise of each, and it expands the measures of the stable foliation by some factor lambda, and contracts the measures of the other foliation by 1 over lambda. So here's an example, or just a little schematic of what these foliations look like on patches of the surface. So away from, I said these foliations can be singular, but away from the singularities, they just look like, you know, these sort of rectangular foliations. One is in blue and one's in red. So maybe the map expands the leaves this way and contracts them in this direction. They can also have these prong-like singularities on the surface. All right, just to give you an idea if you haven't seen this before. Okay, but we're going to focus on this lambda. This lambda is always some real number bigger than 1, and it's what's called the stretch factor, or the dilatation of the map. And we'll use the notation lambda of J just to remember that this is in reference to the monodromy of R naught J. Okay. So the idea is that we're going to try to control the dilatation, lambda of J, in terms of K. Right. And why do we want to do that? Well, because there's this theorem, I'll credit Khovanov, there are many different ways of proving it, which says that if you fix a surface S and you fix some real number M, then up to conjugation, there are only finitely many pseudo-Nassau homeomorphisms of the surface with dilatation less than that constant M. So if you can bound the dilatation by some universal constant, then, well, there are only finitely many pseudo-Nassau maps up to conjugation you have to worry about. All right. So then, yeah, the goal, as I said, is to bound lambda of J purely in terms of K, right? And if we can do that, that'll imply that there are only finitely many possible J, ribbon concordant to K, fiber J, since J is determined by its complement, as I said before, and the complement is determined exactly by the conjugacy class of its monodromy, right? So if you bound the dilatation, Khovanov says there are finitely many possibilities for the conjugacy class of the monodromy, hence for the not complement, hence for J itself. All right, any questions about the strategy? All right, so, you know, how do you get a handle on the dilatation of this monodromy? Well, one way to do it, and this is a way that a dynamicist might think of doing it, is you look at iterates of the map, and you count the number of fixed points of those iterates, and you take a limit of this type. And it turns out that that recovers the stretch factor, the dilatation. All right, so that's what we're going to try to do. So first of all, we want to understand something about the number of fixed points of phi to the n. Well, how do we understand phi to the n? Well, if we take Jn to be the lift of our knot J in its n-fold cyclic branch cover. So you take the n-fold cyclic branch cover, and you lift J to that n-fold cyclic branch cover. That's another fibered knot, J sub n, and the monodromy of that fibered knot is precisely phi of n. Okay? Okay, so we're also going to consider lifts of the knot K and lifts of the concordance itself in its branch cover, the branch cover of S3 times I along C. And as I said, yeah, the monodromy of J of this lift is freely isotopic to phi to the n. Okay, and then we want to get a handle on the number of fixed points of this map. And for that, we're going to use this very nice theorem of Ni and Gigini and Spano, which says that actually, if you have a fibered knot, the number of fixed points of its monodromy is bounded above and really, if you're careful, detected by the knot floor homology of the knot. So knot floor homology provides a bound on the number of fixed points of its monodromy for any fibered knot. So in particular, for this fibered knot J to the n, this gives us a bound on the number of fixed points of phi to the n. Okay. So that's what we're going to use to try to control this dilatation. And we want to control it, remember, in terms of the knot K. All right. So as I mentioned before, the concordance complement from J to K is a ribbon cobordism. It's made of 4-dimensional 1 and 2 handles. The same is true for the complement of the lifted cobordism and its n-fold branch cyclic cover, because this complement is just the n-fold cyclic cover of the complement of C. And so the 4-dimensional 1 and 2 handles just lift. So this is a ribbon cobordism in the sense that I described earlier. And if n is a power of 2, it's actually a Z2 homology cobordism. So this just means that the inclusion-induced maps on homology with Z2 coefficients from the two ends are isomorphisms. Okay, so this is sort of a technical condition. Why is it important? It's important because of this nice work of Daimi, Lidman, Velovic, and Wong, which says that if you have a Z2 homology ribbon cobordism between two knot complements, then in fact, you get an injection on the knot floor homology. So this is a generalization of Ian Zemke's result for knots in S3, right? So in particular, when n is a power of 2 in our setting, we see that the knot floor homology of Jn injects into the knot floor homology of Kn. Okay. So now let's put all these pieces together. So we've already said by Gigini, Spano, and Yi that the number of fixed points of phi to the n is bounded by the knot floor homology of Jn. And when n is a power of 2, this corollary above tells us that that's bounded by the dimension of the knot floor homology of Kn, right? And so we've bounded the number of fixed points of phi to the n in terms of the dimension of the knot floor homology of the lifts of K. All right. So we're very close. So really what we have to do now is just understand how this group grows as n approaches infinity. And there are many ways to do that. Here's a rough way, which is easy to describe. So let's say that K has a grid diagram with arc index delta. So here's an example of a grid diagram. If you haven't seen it, this is a grid diagram of a trefoil. And it's just a way of writing a knot as a union of horizontal and vertical segments. So the verticals pass over the horizontals whenever there's a crossing. And Peter mentioned this in an earlier talk as the input for computing knot floor homology combinatorially. So the arc index, if you have a grid diagram, is just the number of vertical strands. So in this case, it's 5, which is the same as the number of horizontal strands. Okay, so suppose K is a grid diagram with arc index delta. One of the first things that Adam Levine did, maybe the first thing, so this is baby Levine, is he he showed that if this knot, Kn, the lift of the knot in its n-fold cyclic branch cover, then has a multi-pointed Heegard diagram so that the intersection of the alpha and beta tori is, well, it has delta factorial to the n intersection points. And these are what generate the Heegard floor complex. And so the Heegard floor complex has rank equal to delta factorial to the n. And so the homology of that, after normalization, the knot floor homology of this lifted knot then has dimension less than or equal to that number, delta factorial to the n. And so if we put all these things together, then we see that the dilatation, right, we could describe it in terms of this limit, and we might as well take this limit along powers of 2. And the term that goes inside here, we bounded on the previous slide by the dimension of the knot floor homology of k at the n. So when we take the nth root, we just see that that's less than or equal to delta factorial. So we've bounded the dilatation of the monodromy of our knot j in terms of this quantity which depends only on k, right? And this is what allows us to conclude there are only finitely many fibered hyperbolic j that are ribbing concordant to our fixed knot k. All right. So, I mean, you can ask about, there are lots of questions. One natural question is, what about non-hyperbolic fibered knots? We imposed this hyperbolic condition in part because we could say then that the monodromy of J had to be pseudo-Nosov, and we could understand it by bounding its dilatation. So if it's not hyperbolic, then Thurston tells us that it's either a torus knot, and in this case, it's very easy to see there are only finitely many torus knots ribbing concordant to a fixed knot K. And the reason is just that by Zemke, for example, the genus of J is bounded above by the genus of K, and there are only finitely many torus knots in each genus. Okay, so you're sort of done if you assume that J is a torus knot. And the harder case is that J is a satellite knot. Okay, so I said that there's this Nielsen-Thurston classification of surface homeomorphisms. You're either periodic or pseudo-Nosov or reducible. And in the satellite case, that's the case in which the monodromy is reducible. And so what does that mean? That means that it fixes setwise some multi-curve, some embedded multi-curve on the surface. Well, this multi-curve cuts the surface into a bunch of components. And what happens on each component? Well, the components of the multi-curve might be permuted around the surface. It's just fixed setwise. And so the components of the complement may also be permuted around the surface. But if you take one such component and apply the monodromy enough times, then it comes back to itself, right? So some power of the monodromy sends each component back to itself. And then let's suppose that M is the least power that does that, okay? And then what you can say is that phi to the M from F to F is then either periodic or pseudo-Nosov, okay? So that's what happens for reducible monodromies, which are what you see in the satellite case. All right, so how do we deal with this? So first of all, let me just call one of these components periodic or pseudo-Nosov according to whether this map is periodic or pseudo-Nosov. So, F is some subsurface of S, and the genus of S is bounded. So the topology of F is constrained. And so if F is a periodic component, there are only finitely many possibilities for what this map could be. And so then one idea is to try to constrain, try to bound the dilatation of this map for the pseudo-Anosov components. And in the same way as before, use that to say that there are only finitely many possibilities for what this map can be in the case of a pseudo-Anosov component. So whether the components are periodic or pseudo-Anosov, you've constrained what the possibilities are up to a finite list. And then you'd like to say, okay, well, there are these finitely many possibilities, and there are finitely many ways of piecing them back together to get the monodromy of a knot in S3. So that was one idea, to try to constrain the dilatations on the pseudo-Anosov components in terms of K. And the naive thing to do, ooh, this is ugly, but, well, so the dilatation of this map, it's less than or equal to the dilatation of the full map, which makes sense, even though this is reducible. And we know we can compute this as some limit here, as before. And then by the Gijinian-Spano result, we can bound that by a limit involving knot-floor homology of these lifts of J, as before. The problem, and the thing that's missing, is that we can't then bound this in terms of the knot K, as we could in the previous case. And the reason for that is because how do we bound this in terms of the knot K? Well, we used that beforehand. We used that the corresponding concordance exterior was a Z2 homology cobordism. And that just doesn't have to be true. I mean, depending on what M is, it just needn't be a Z2 homology cobordism, and there's basically no way to recover this strategy that we could come up with. So that's not what we do. We do something, well, different. And the key new ingredient, and it's not immediately obvious why this is so useful, perhaps, is a satellite inequality in knot-floor homology. So maybe this is of independent interest. So if J is a satellite knot, and let's say it has companion knot Z, and let's suppose that its pattern has non-zero winding number, then what we show is that the dimension of the knot-floor homology of the companion is less than or equal to the dimension of the knot-floor homology of the satellite. So you might expect this. I mean, in some sense, the companion is like a simpler knot than the satellite knot itself. So you'd kind of expect this inequality. But I think this was only really known for maybe satellite knots with 1-1 patterns or something like that before. And the proof, I won't really get into it, but it uses the immersed curves formulation of bordered Hager-floor homology due to Hanselman, Rasmussen, and Watson. And if you're familiar with their work, so they used this immersed curves formulation to prove a pinching inequality. So if you have 3 manifolds with torus boundary, then there's a degree 1 map from one of these manifolds to a solid torus. And what you'd expect is that there's an inequality in Hager-floor homology between the Hager-floor homology of the glued manifold and the one where you just glue but replace one of these with the solid torus that one side pinches down to. And that's true, and they proved that using the immersed curves formulation. And our proof of this satellite inequality is modeled on that. Okay. So if you don't know about this immersed curves formulation, then that was meaningless. So then we combine this satellite inequality with the things that I had described earlier to prove this technical theorem. Okay. So it's a little bit much to digest, but what it says is if I fix a number m and g is going to stand for genus, then there are only finitely many genus G fibered knots in the 3-sphere, so that the dimension of knot flow homology of their lifts is bounded above by this exponential with base m for infinitely many primes n. Okay. So from this, we can prove the finiteness result for general fibered satellite knots J by some inductive argument. And the basic outline is this. Suppose we have our knot K. Let's say it has genus G, and M here you're really supposed to think of as delta factorial, the arc index factorial. All right? Okay. And what we show is that there's an infinite set of primes, which depends only on K, so that this concordance complement is a Z2 homology cobordism. This is the technical condition we needed to show that there's an injection on the knot flow homology. And it's a Z2 homology cobordism for every n in this set, and whenever J is ribbon concordant to K by a ribbon concordant C. And so in this case, that proves the theorem that we wanted. Right? Because the theorem here says that, well, the knot flow homology of the lift of J is bounded by m to the n, okay, for infinitely many primes. And the theorem here says that there can be only finitely many fiber knots of each genus satisfying that, right? And the genus of J is constrained by that of K. So that tells us in the end that we only have finitely many fibered ribbon predecessors of K. Okay. So that's the idea. So one question that I think is interesting is does this finiteness theorem hold if you remove this fibered hypothesis on J? And if so, then the point is that it would prove our finiteness conjecture in full. You could use it in the same way that I've described to say that for any fixed K, there are finitely many ribbon predecessors. And if you knew that, then it would imply this conjecture of Gordon that I highlighted at the beginning, that you can't have infinite descending chains of ribbon concordant knots. Okay. So I'll say one last thing, and quite a bit early, which is that there's been a lot of work relating the dilatation of monodromies of fibered knots to the volume of their complements, to the volume of the corresponding mapping tori. And in particular, Kojima and McShane worked out a very explicit inequality with very concrete and nice constants, which bounds the volume of the complement of J in terms of the log of the dilatation. And so using that, we can also get this corollary. So if we have a knot K of genus G, arc index delta, and we suppose that J is a fibered knot ribbon concordant to K, then the volume of the knot complement of J is bounded by this quantity, which depends only on the knot K. So it's not quite the monotonicity of volume conjectured by Gordon, but at least it's a bound on the volume of any fibered ribbon predecessor of the knot K, just in terms of topological quantities, depending only on K. Okay, so this is all I have to say.
Thanks. Okay, do we have any questions?
Can you use this to show that for a fibered knot, it's decidable if it's ribbon?
No.
Okay.
So one thing I'll mention is that so I'll say a couple things, but the answer is no. But one is that instead of thinking of the relation which is ribbon concordance, I could think of the relation which is strong homotopy ribbon concordance, or as Maggie likes to call it, handle ribbon concordance. And the same finiteness proof works there. So in other words, if I fix a knot K, then there are only finitely many fibered knots J that are handle ribbon concordant to K. The other thing which is more along the lines of what you asked is that this gives you in principle an algorithm, if I fix some knot K, to generate a list of knots which contain all of those which are ribbon concordant to K, all of the fibered knots that are ribbon concordant to K, right? Because I get this bound on the possible dilatation, and then if I have a bound on the dilatation, well, like I said, there are only finitely many possible monodromies up to conjugation, and you can actually enumerate them. There's a way to enumerate them. So you can get a list of all potential fibered ribbon predecessors, but there might be extras in there. A database for these ribbon concordances. I have no idea. So another thing I'll say is that one of the nice things in the Egel-Wren paper, which proves a related result by different means, is that I think one of the things that Chiu did in that collaboration is he really modified this Casson-Long algorithm for deciding whether a monodromy extends over a handle body. He modified it to an algorithm which helps you understand whether a monodromy extends over a compression body, which is the condition they use. And so, I mean, what I've heard is that Nathan Dunfield is going to implement that algorithm, and that should help produce the kinds of data that I think maybe you're talking about.
So maybe 1 or 2 slides ago, you had this theorem with, this one. So you mentioned earlier the result of Levin that for every knot you can find a presentation, and so the growth of the dimension of HFK hat is at most exponential if you pick a grid diagram, but somehow this M is probably very huge because it depends on the arc index. Does your theorem with Hanselmann and Sivek also use a grid presentation, or do you use another method to find this exponential base?
I mean, the reason we use this result of Levin is just because it's somehow like the easiest to state. I mean, there's a much better bound on the exponential growth of the knot homologies of the lifts of K. But that doesn't come into play. We just use that result. Like the thing that we prove with Hanselmann, this knot floor satellite inequality, is that what you're asking about? That doesn't use grid diagrams at all. For there, we're just using immerse curves. So we consider, so if you want to understand how the knot floor homology of satellite knot, well, what you can do is you can write down the immerse curves for the exterior of the companion knot. That's some compact curve. And then you can write down an immerse curve for the pattern knot in the solid torus. So The Bordin invariant of that is not an extendable type D structure, so that curve is not compact. It might have compact and some non-compact components, and that's a little bit tricky. We had to argue some things. But then the knot flow homology of the satellite is just given by the pairing of those two curves. Okay? So we have the companion complement, and then we have the curve for the satellite in the solid torus. Now, if you want to just understand, and the pairing of that gives the knot flow homology of the satellite. If you want to understand the knot flow homology of the companion itself, then what you do is you look at the curves for the companion complement, and you pair that with a very, very simple curve for the core of the solid torus. And what we argue is that those two things have fewer intersections than the other two curves. That's where we get our satellite inequality.
Any more questions? Okay, let's thank John again. And okay, so we have, I don't know, 15 to 20 minutes. The next talk's at 12 p.m., so we have about 20 minutes. All right, we sadly have just one talk left, but happily it's Claudius Zibrowius. He will be speaking to us about Khovanov homology and Conway mutation.
Thank you. Hello, everyone. Since I am the last speaker of this conference, I would like to invite us all to say thank you to the organizers for this wonderful event. I want to tell you about a project that started quite a while ago while I was still a postdoc with Liam Watson. So this is joint work with Artyom Kotelsky and Liam Watson. The story starts with an observation of John Conway that he made in the 1950s, 1960s, while trying to compiling knot tables or finding a more efficient way to tabulate knots. And he got stuck at this particular pair of knots. So the story goes, and the knot on the left is the Kinoshita-Terasaka knot, and the knot on the right is now known as the Conway knot. And these two knots, they're related by this operation Conway mutation, which works as follows. You take your link, you intersect it with a 3-ball whose boundary intersects the knot transversely in precisely 4 points. And then what you get inside is some object like this, a Conway tangle. So two embedded strands, properly embedded strands in the 3-ball. And you can choose those 4 endpoints to lie on some great circle, maybe equidistant, and then you can do the following operation. You cut out that tangle, you rotate it by 180 degrees, and then you glue it back in. Okay, and this is the operation that relates these two knots, and it turns out that any two mutant knots are fairly hard to distinguish. A lot of invariants remain invariant under this operation as well. For example, one such invariant is the Jones polynomial, which follows from the fact that, well, any invariant defined by a skein theory has to be also invariant under this operation. And so it's a fairly natural question to then ask, well, whenever you have a new invariant, such as Khovanov homology, well, what about Khovanov homology of these two knots? Conway mutant knots. And it turns out, yeah, these two knots have the same reduced Khovanov homology. But it turns out the story of mutation and Khovanov homology is more subtle, because we had contradictory evidence. Because, well, Stefan Verli in 2003 found a counterexample to mutation invariance. So he found this pair of links that are mutant, and they just have different dimensions if you work over the field of rational numbers. But if you vary the field, then you find that if you work over any field of characteristic 2, then suddenly the dimensions agree, and even the bigraded dimensions agree. And yeah, about 15 years ago, 16 years ago, Stefan Verli and independently Jonathan Bloom, they proved that, in fact, if you work over Z mod 2 coefficients, then yeah, you have mutation invariance. Jonathan Bloom actually proved something more general. He proved that odd Khovanov homology is mutation invariant, so therefore also Khovanov homology with Z mod 2 coefficients is. The result that I want to talk about is a generalization of this theorem to arbitrary fields, but restricting to the class of knots. So the theorem that I want to talk about is that if you perform mutation on a knot, then its reduced Khovanov homology over any field that you choose will remain invariant. Why do I care about this? I'm not that sure, actually. So, I mean, it's an open question, or it was an open question, and yeah, you might think about some applications. So you can think about this. So actually, it's a negative result, right? It tells us that Khovanov homology isn't strong enough to distinguish certain knots. You might view it as a positive result if you say, okay, Khovanov homology is an obstruction to two knots being mutants of each other. But I guess my answer to why I care about this is I care about the technology that goes into the proof of this theorem. And the technology is the theory of Khovanov multicurves. So there's an invariant that I defined together with Liam Watson, who's here, and Artem Kutelsky, and it takes this particular form. So with any object of this form, for any Conway tangle, we associate, with any such object, we associate an object in the Fukaya category of the surface, which is the four-punctured sphere that is the boundary of the three-ball in which the tangle lives. There is one subtle point, namely, well, we have to fix a base point to make this work. And this will play an important role. So in the first part of my talk, I want to review this construction. Where does this multicurve come from? How do we think about this? Okay. Well, we start with a tangle diagram of our tangle with this choice of base point. And then, well, Drobanatan told us how to think of Khovanov homology locally, what the Khovanov homology of tangles, not necessarily four-inner tangles, arbitrary tangles, what that is. Namely, we apply this usual cube of resolutions construction that gives us this cube at whose vertices sit crossingless tangles, and then the arrows, the edges of this cube, they're labeled by some morphisms inside some category called the cobordism category. And it turns out you can make precise the notion, you can talk about the notion of chain complexes, bigraded chain complexes over this category. And he showed that this is indeed an invariant. He also then showed us how to simplify this object. Okay. Namely, whenever we have a closed component in a closed circle on one of these vertices, we can remove that at the expense of tensoring or having two copies of the resulting tangle. So he called that delooping, and in this particular example, you get this chain complex on the right-hand side. So now at the vertices of this graph, of this labeled graph, we have crossingless tangles without closed components, and the edges are labeled by some morphisms in this cobordism category. I want to go into the details. So how does this cobordism category, what does that look like? And I want to take this, this chain complex as an example. So what are these arrows? Well, one of these arrows is fairly simple. It's just the ordinary saddle cobordism. Here's a picture. The other one is more interesting. It's a linear combination of cobordisms between these two horizontal tangles. Namely, it is, well, the identity cobordism with a tube connecting the two components, and then minus the cobordism obtained from the identity by increasing the genus of one of its components. And this is the point where we make use of the base point on our tangle end, this violet point. By introducing this notation, a dot on a sheet in our cobordism has the following very explicit, it's just notation, has this following meaning, namely, it is the linear, is this linear combination. Take the sheet containing the dot, connect it to the distinguished sheet, the one with the base point. That's the first cobordism, and then subtract from it the cobordism obtained from the original one by increasing the genus of the distinguished sheet by 1. Okay, and these are two interesting morphisms in this category, and it turns out that this is all you need to understand. Okay, these two morphisms, they generate the entire full subcategory generated by the two crossingless tangles without closed components. So we have this description of this cobordism category in terms of this algebra B that we called the Banatan algebra, and yeah, it has this description in terms of this quiver. So we use this isomorphism and to rewrite our chain complex. As follows, we just replace the vertices by now the solid dot and the hollow dot, and the dot cobordism and the saddle cobordism by S and D. And we call the resulting invariant, there's now a chain complex, a type D structure, over this Banatan algebra B. The next step is the following. We want to get Khovanov homology. And it turns out for that, well, the Cyrillic D of T invariant on the left, that is something more sophisticated. It's actually Banatan homology, the equivalent of Banatan homology. And so to get down to Khovanov homology, we have to set that extra variable equal to 0. One way of doing that is just taking the mapping cone of the identity map times this element G, which is, you can express in terms of the generators, is just S squared minus D. So in our example, we have this chain complex on the left, and then just take 2 copies of it and connect it by the identity map times this element G. I denote this new invariant that we get by Cyrillic D sub 1. Okay, so now we have these two tangle invariants, and well, whenever I have 2 tangles, I can take their union and obtain a link. And I'm taking this union in this, maybe you would say, a slightly complicated way, in such a way that the 2 base points, that they're identified. So I have 1 base point on this link. And, well, the algebraic Lewing theorem says that I can recover the reduced Khovanov homology of this link, of this based link, as the homology of the morphism space between these 2 chain complexes associated to the tangle T prime. There I use the one with the mapping cone, and then the invariant of T where I don't use the mapping cone. Okay, so this follows almost immediately from Banatan's gluing formalism. Yeah. Any questions up to this point? Okay. So we now have a way to decompose our knot into 2 tangles, and then mutate one of them, and then see what happens to the Khovanov invariant. Okay. In order to do that, well, we had this base point in our construction that gave us the isomorphism between the cobordism category and the Banatan algebra. And so let's look at this base point again, and see how the invariant depends on that base point. So here's again this dot cobordism. Okay, so I have my violet base point down there that distinguishes one of the 2 sheets, the one at the bottom, and then I have a dot on the other sheet. Okay, and as I said earlier, this is just this linear combination. I connect the sheet with a dot to the distinguished sheet by a tube and subtract the cobordism obtained by increasing the genus of the special component. And now, for those of you who are familiar with the cobordism category, well, you might see what's going on here, or what the next step is. We have relations in this cobordism category. Namely, we have the sphere relation that says whenever I have a cobordism that contains a sphere, then that whole cobordism is set equal to 0. And the other relation was more complicated. It involved 4 terms that Banatan called the 4 tubes relation. And when we apply this relation, we obtain this equality. This is exactly the 4 tubes relation. And now we interpret the right-hand side. Okay, if there we don't need a base point anymore. We only needed the base point in order to make sense of this dot notation. Okay, and now we choose a different base point, namely on the other, for example, on the other side when we mutate. So, well, we obtain again a dot cobordism, but now it has a minus sign. Okay. And it's really this observation that explains all of the complicatedness when you look at mutation and Khovanov homology. Okay, so we now have this corollary from this observation that for any pointed Conway tangle, right, we can look at the invariant of its mutant, and we can compute it from the invariant of the original tangle by simply adding minus signs to all the dot cobordisms, i.e. to all the Ds in our Banatan algebra. Okay, so now we can try to prove mutation invariance. Okay, so here's the setup. We have our 2 mutant links. Okay, a union of T and T prime, and T prime, and then mutant of T. We rotate everything by 180 degrees. And we apply our pairing theorem, our gluing theorem. And in the first case, well, it looks like this. Right? We look at the homology of the morphism space from the mapping cone of the first invariant to just the invariant of the second tangle. And we do the same for the other link as well. And then we apply the corollary that was on the previous slide, and we see this morphism space. And so the only thing that has changed is we have added minus signs to all the Ds in the invariant of the second tangle, of the tangle T. So now all that remains to study is, well, how do these 2 morphism spaces, how do they compare? One immediate consequence from what we've done so far is that, well, if you work over characteristic 2, then there are no signs. Okay, so these 2 things are isomorphic. So we get this as a corollary. The invariants, the tangle invariants don't change. And therefore, we get a new proof of Stefan Verdi's and Jonathan Bloom's result. And our proof, I think, is fairly close to how Dror Banatan originally thought about mutation. So he had some hunch that that it should be true, and he had some ideas how to prove it. The only thing that was missing was the right basis of this cobordism category. Okay, that was the only thing that was missing. He could have done this 20 years ago if he had had this basis. Okay, so let's look at some examples. So here's a rational tangle, the two-twist tangle, this tangle here. And let's see how mutation affects this tangle invariant. Okay, so we mutate this. So we add minus signs to all the d's. There's one d. And, well, we now ask, are these two chain complexes over this Banatan algebra, are they isomorphic? What do you think? Yes, they should be. Well, they should be isomorphic because I can do a base change to get rid of the minus sign. Okay, and another way of seeing that this should be mutation invariant is simply that if I take this tangle and I rotate it, nothing changes. It's the same tangle. Maybe I swapped the colors, blue and white, but that's it. Okay, so that's easy. Okay, let's look at a more complicated example. So this is the tangle that we mutate along when we look at the Kinoshita-Terasaka and the Conway knot. And again, we mutate. We add minus signs to all the d's. And again, we can do a simple base change to get rid of all the minus signs. Okay, so these are also isomorphic. So that explains why these Khovanov homologies. So these two knots are isomorphic. Okay. Now let's look at the tangle that was involved in Stefan Wehrli's early counterexample to mutation invariance for links. So there we had the split tangle, so the trivial tangle, but the trefoil knot tied into one of its components. Its invariant looks like this. It has it's a direct sum of two such chain complexes. And we mutate, and we get from minus d to plus d. And these two chain complexes are not isomorphic. They're not even chain homotopy equivalent. Okay. And so this explains why, it doesn't prove that these two things are different, but it's indication that something interesting is happening here. Okay. So what we've seen so far is a tangle invariant that takes values in finitely generated bigraded chain complexes over this Banatan algebra, over this quiver algebra. And in fact, we get two invariants. One is just the mapping cone of the other. And I think that's all I wanted to say. Okay, and we know how mutation works. We just add minus signs to all the d's in the first invariant. Okay. Any questions up to this point? Okay. So what we need to understand is somehow how do these chain complexes behave when I add these minus signs? Okay, when I change the minus signs of all the d's. Well, here's a useful fact from higher representation theory that is maybe true enough since I haven't defined any of the terms. So every chain complex over this Banatan algebra is chain homotopic to a direct sum of cyclic and linear chain complexes over B. What do I mean by that? Well, I won't define this, but I just illustrate this by example. So cyclic chain complex, what I mean by that is it has a graph that looks like a circle, a circular graph. Okay, so here are two cyclic graphs. And a linear graph is, a linear chain complex is just one that is represented by a linear graph. Now these linear graphs, they're fine when we think about mutation, because there we can always do this base change to get rid of any coefficients, actually, if we work over fields. Okay, so this is always mutation invariant, whereas these cyclic graphs, there we can also decide when they are mutation invariant, namely when the number of d's that we see on each cycle, when that number of d's is even. Okay. Okay. And so that's the next part of our construction step. We clean up our chain complexes. we get, well, for the first complex, that's already linear, so there's nothing to do. And the second complex, this mapping cone here, that doesn't look like a cyclic graph. Okay, but we can simplify it. We can choose a different basis, and we get this graph on the right-hand side. Now, where does this fact from representation theory come from? Okay, so it comes from this perspective, the symplectic perspective on this algebra B. So here's again this quiver that describes B as a path algebra modulo these relations. And it turns out that this is isomorphic to the endomorphism algebra of two objects, namely these two arcs in the four-punctured sphere, considered as objects in the wrapped Fukaya category of this four-punctured sphere. I write the four-punctured sphere as the three-punctured disk here, and we'll come to that later on. Now, there's a general correspondence that was proved by Haydn, Katsakov, and Kontsevich that classifies chain complexes over not just this algebra, but algebras associated with surfaces plus some extra decoration in terms of the Fukaya categories of those surfaces. So here's, okay, so let's move on. So here's this classification result. Chain complexes over these algebras, gentle algebras, in this case B, up to chain homotopy equivalence, they are in one-to-one correspondence with multicurves, with objects, with curves, possibly immersed curves, on our surface. In this case, this three-punctured disk. Here are some examples. So again, our linear complex from earlier. It is represented by this arc. It's actually embedded. That connects these two tangle ends, these two punctures of the disk. Here's the second example that we had earlier. It is a cyclic graph, and so it corresponds to a closed circle embedded into, or immersed here in this case, immersed into this three-punctured disk. Now, there was this business about signs, right? So this is also a chain complex over B. Yeah, but it now has this minus sign, and I claimed earlier that, well, if you do this, if you add just a single minus sign, then you get something that is not chain homotopy equivalent to the original. So there's something missing here on the right-hand side. So I somehow need to record this minus sign, and this is done by use of a local system. In general, a local system is, you can think of this roughly as a matrix, an invertible matrix that you consider up to conjugation. In our case, we'll be only concerned, we'll only see one-dimensional local system, so it's just a non-zero element of your ground field. Okay, so we have this correspondence, and now we are almost there. We just apply this correspondence to get from chain complexes over B, the cyclic or linear chain complexes over B, to multicurves on the three-punctured disk. So that's our last step. We use this correspondence and get these two objects in the Fukaya category. And as a final summary, well, if we now think about mutation, Conway mutation, then, well, the only thing that changes is the minus signs on these, on the Ds. Okay, so overall, the local system might change by a sign. Okay, but that's the underlying curves themselves, they stay the same if you mutate. Now, there's a reformulation of the algebraic gluing theorem in terms of, well, these objects in the Fukaya category. So again, we look at this tangle decomposition of our link, and we can compute its reduced Khovanov homology as the Lagrangian Floer theory of the two curves. In the first case, the Khovanov immersed curve, so that corresponded to the mapping cone of G. And in the second case, we use this Banatan curve that corresponded to not taking the mapping cone. What is this Lagrangian Floer homology? What is it? It boils down generically to counting intersection points, minimal intersection points between two curves. So here's an example, the Conway sphere decomposition of the trefoil knot. The blue curve on the right is the invariant that we saw earlier for this two-twist rational tangle, and the figure 8 curve, the red curve on the right, is the invariant of the one-crossing tangle. And it just now taking the Lagrangian Floer homology amounts to, looking at those intersection points, they generate the Floer homology, and in this case, that's the entire homology and the differential vanishes. Okay, any questions up to this point? Because we're now ready to prove the main theorem. Yeah, that's a question.
Just to understand the picture, is the red curve self-intersecting or is it going right?
It's self-intersecting, yeah. Yeah. In fact, all of the components of the Khovanov invariant intersect themselves. Yeah. Okay. Then let's prove the theorem. Okay. So what do? We take our two mutant knots, decompose them into these tangles, T prime and T, mutate T, and we apply the gluing theorem and express the Khovanov homologies in terms of their Lagrangian Floer homologies. Okay, the first component stays the same, and only the second one is mutated. So there we see the minus signs. So let's write the Banatan multicurve in terms of its components. So here the gamma I, those are the underlying local, the underlying curves on the surface, and then xi, those are the local systems. So just think of some coefficient in our field, non-zero element of the field. We mutate, so the invariant of the mutant tangle has exactly the same number of components. The underlying curves are the same, only the local systems, they change. So there we potentially get some minus signs. Okay, and now, well, Lagrangian Floer homology is additive, so we can look at everything component-wise. So it suffices to look at individual component of the Khovanov invariant of T prime, gamma prime, and look at its pairing with each individual component of the Banatan homology, Banatan curve of these two tangles, and see what happens. Okay, there are two cases here to consider. The first case is very simple. Suppose that the underlying curves of gamma prime and gamma I, that they don't coincide, that they're not homotopic to each other. Well, in that case, it turns out that the Lagrangian Floer homology of them is more or less independent of the local systems. Okay? As long as the dimensions of the two local systems that he put on the curves have the same dimension, as long as that is true, then the Lagrangian Floer homology won't see any difference. Okay? So in particular, a sign flip won't affect the outcome. Okay. And this is somehow the point where the example of Stefan Werli, where that failed. So somehow he got as unlucky as possible. He had two parallel curves, curves that coincided except for the local system. Okay, so this is the easy case. So what happens in the other case? If I have two curves whose underlying curves coincide, but the local systems might change, and then one of them has this sign flip. Well, at this point, you're stuck. I mean, we were there at this point 6 years ago. And yeah, then you need some idea. Something crazy happened. So it's this, we have a full classification of components of the Khovanov invariant of the tangle. We can have a complete list using finite data. So this theorem, which is actually the main theorem of the talk, this theorem says that the Khovanov invariant of a tangle T, that any component of it is one of two types. The first we call rational, second we call special. And I'll say in a moment why we chose this terminology. What we then also need to determine a component is its slope, so some element in the rational projective line, and some length, so some Lj prime here. We know that, well, the rational components, they can, in theory, be of any length, though in practice we've only seen length 1 and 2. And the special components, they always have even length, okay, whatever that means, just some parameter. Okay, so we now see every curve, every component of this Khovanov invariant can be described by 3 parameters, namely its type, rational special, its slope, P over Q, and its length. And then some grading. I'm omitting all the gradings here in this talk. Okay. Why do we call these rational components? Well, because there are these things, objects called rational tangles. So this is an example of a rational tangle. It's obtained from the trivial tangle by just twisting the endpoints. And there's a theorem of John Conway that classifies these objects in terms of the rational projective line. Okay, so the slope appearing in this theorem is something very natural associated with a full-punctured sphere. Okay, and turns out that these Khovanov invariants, they detect rational tangles, and they're equal to exactly these rational components that we saw on the previous slide. Okay, so if you have a tangle T whose Khovanov immersed curve invariant consists of a single component which is rational of length 1 and slope P over Q, then that tangle had to be the rational tangle of this slope P over Q. A new theorem that we also prove in our paper from earlier this year is that these rational components detect how the tangle ends are connected by the tangle. More generally, whenever you have a rational component of odd length, this is important, odd length, either in the Khovanov multi-curve invariant or in the Baldwin curve invariant, then you know how it connects, how T connects the tangle ends, namely in the same way that the rational tangle of slope P over Q connects the tangle ends. Okay. And then we need a third observation to finish the proof, namely that any curve of even length won't change under mutation. Now, I'm just claiming this here, but this is really an easy observation. If you draw the chain complexes corresponding to these curves, so that's a very, very easy observation. So somehow, what this says in light of the previous classification result is that, well, we have these components. Okay, the special components always have even length. The rationals might have odd or even length. Okay, we care about mutation. Well, the special components, they're mutation invariant. The rationals of even length, they also don't care about mutation. They remain invariant. And then the only curves that might change their local system under mutation are precisely those that detect the connectivity of the tangle. So now we can look at this second case. So suppose we have two curves, the two curves, gamma prime and gamma I, are identical up to local systems. Then, well, the geography result for Khovanov, the Khovanov invariant says that gamma prime has to be either rational or special. So therefore, well, also gamma I is either rational or special. Then, well, we know that we're doing mutation on a knot. So that tells us that the connectivities between these two tangles, they can't be the same. Okay, if they both were connected, were connecting the tangle ends like this, then we would have a link. Okay, if they both were like this, then we also have a link, and similarly this. Okay, so we know the connectivities are different, and so therefore, yeah, the gamma I can't be a rational component of odd length. Okay, because the connectivities are different. So yeah, also the rational components have to be even length. And now we only have components of even length, and they are mutation invariant, so there the local system does not change at all. Okay. Any questions? Okay, no? Okay. There, you can improve on this result by observing that even the rational components of odd length have an even number of these d's if the connectivity of the tangle is this connectivity. Okay. If you have this connectivity, then mutation does not preserves the components of the link, if this is embedded in some bigger link. So we can improve the same arguments on the previous slide, give you this improvement that, in fact, Conway mutation preserves the Khovanov homology of over any field if the mutation is component preserving. To give you an example of a mutation that doesn't preserve components is, well, exactly this example from earlier, Stefan Verli's counterexample. We see that, well, this mutation here doesn't really do anything, right? It's a mutation along a trivial tangle, except that we've connected some in a trefoil knot on one component. So that component switches component. So there's not component preserving. Okay, so we have this, this improvement. Okay, so it remains to say a few words about this classification result. That was the key ingredient to this proof that I've presented. Look. Okay, so why does the Khovanov invariant only see this very small part of the Fukaya category that these invariants could live in? Well, we go back to this perspective on this Banatan algebra. Okay, I said this is isomorphic to the endomorphism algebra of these two objects in this wrapped Fukaya category. In general, objects in this Fukaya category, they are some immersed curves that are unobstructed, meaning that they don't have any of these teardrops. So they don't bound. They're not no such disks. What you can do here is, well, you have this boundary. You have this base point, or this boundary of the disk, and you can fill that in by a smaller disk. Okay, and now you have a three-punctured sphere. The endomorphism algebra of these two objects does not change when you do this, but it gets some additional structure. It gets the structure of an A-infinity algebra. And here are some of the higher operations. Okay, so if you see a ds, then you have this higher multiplication map that tells you this is equal to 1, not 0. And this classification result from earlier, this classification result here of Haydn, Katsakov, and Kontsevich, this also generalizes to other surfaces, I said. Okay, only there you need to, well, potentially work with A-infinity algebras, and that's exactly the case here. So here we had this curve. Okay, here we have another curve in the three-punctured disk. And they're both of them are objects in this Fukaya category. Yeah, none of them, they're unobstructed, they're objects, and there are the chain complexes. But if I now fill in this puncture, then I replace the Banatan algebra, the ordinary algebra, by an infinity algebra. Right, and on the right-hand side, I fill in this disk. And now it turns out, now this blue curve bounds one of those fishtails. It has one of these fishtails, and so this chain complex on the left-hand side, that is not a chain complex over this A-infinity algebra. An algebraic way of seeing this is that, well, there we have exactly the sequence ds in the chain complex, and that was 1 and not 0 in the A-infinity structure. So that gives us some hope, maybe, that by putting extra structure on this algebra, you can get restrictions on what kind of curves can appear as invariants of tangles. Okay, so if there was some way to define this tangle invariant, not over the Banatan algebra as an ordinary algebra, but some way to extend this to a chain complex over this A-infinity algebra, then we would know that there are no such fishtails, there are no such immersed curves that wrap around this special puncture. Okay, so where do you get such an A-infinity structure on the cobordism category? Well, we don't have a good answer to that. We don't have a good answer to that. I think that's an interesting question. How do you define A-infinity structure naturally on the cobordism category? But here's another way to do this. So here's a theorem of Abuzait, Oru, Efimov, Katsakov, and Orlov, which has this fancy name, homological mirror symmetry for the three-punctured sphere. It says that there is a quasi-isomorphism between the Banatan algebra equipped with this A-infinity structure to the DG algebra, which is the endomorphism algebra of two matrix factorizations. Okay, so there, I can try to use the pointer. So there we have one matrix factorization. That's the matrix factorization that we will associate to the vertical trivial tangle. And then we have the second matrix factorization that we associate with the horizontal tangle. And then you can try to build a cube of resolutions, okay, from these matrix factorizations. And in fact, this is nothing really new that we did. There were already definitions out there of Khovanov homology using matrix factorizations. But we modified those constructions to give us the right algebra. Okay, we wanted to have the most general statement as possible. Okay, so this is just a DG algebra. Okay, and if you take its homology, you get exactly Banatan's algebra, but the homological perturbation lemma then tells you are there possibly higher operations. And these turned out to be quasi-isomorphic to the A-infinity operations on B-infinity. So the proof strategy of this geography result that says components of the Khovanov immersed curve invariant are classified by their type, slope, and length. It goes as follows. Well, down there we have the construction that I talked about earlier. So we start with a cube of resolutions. We end with this chain complex over this Banatan algebra. And now we'd like to extend this to some type D structure, some twisted complex. I think that's the right terminology. Over this B infinity category. In fact, we slightly modify this B infinity algebra to have an additional variable for all the higher multiplications so that we have this algebra map that is just setting u equal to 0, just forgetting all the higher operations. Okay. So we'd like to get up there, and, well, as I said, we use matrix factorization, we use homological mirror symmetry, and define take this cube of resolutions and associate with each vertex a matrix factorization and the edges of our cube. They're just maps between matrix factorizations that generalize saddle cobordisms. And then we prove analogous result to the delooping isomorphism of Banatan in this setting of matrix factorizations. And then we make sure then that the result really coincides with the cobordism category once we forget the higher operations. Okay. Thank you very much.
So thank you. Any questions?
So maybe this is not a fair question, but what happens when you have 6 points meeting the sphere? Do you have a...
Yeah, that algebra is more complicated to understand. We don't know. Well, you can write down a quiver, modulo relations, but I certainly don't understand. I don't have a symplectic interpretation of that algebra.
But would you expect a classification of?
I wouldn't expect a simple classification as in here, because the algebra is not gentle. And so there's not just, it's not we're not describing we're not looking at the Fukaya category of the surface in that setting. It might be some high-dimensional symplectic manifold, and that could be true, some 4-dimensional manifold, and then we'd looking at surfaces, but Lagrangians, but it's not clear to me sort of what a classification result might look like for those objects. I don't know. It's a good question.
What are the difficulties with doing integer coefficient instead of field?
Yeah, that's a good question. So the main difficulty is that this classification result, maybe I'll go back a couple of slides. This classification result just over the, this classification result of Heiden-Katsakov and Kontsevich is not true over integer coefficients. And you just suddenly are in the field of number theory, and that's scary. I don't think you can expect any classification result like this if you work over integers.
Is it possible that there should be a similar lift to this matrix factorization ring corresponding to SLN homology instead of Khovanov homology?
I would expect so. This is, again, a long project with Lukas Levak. We were looking at SLN homology and these tangles, and doing some computations of those morphism spaces, and it seems that we get exactly the same algebra, except that there are additional variables that we just adjoin. Okay, so we get the Banatan algebra adjoins some finite number of variables. And then the question is sort of, what do you do with those variables? Well, if you want to apply this classification result, then you might, I don't know, forget all of them, set them all equal to 0. That would be one choice. Another might be setting them equal to 1, then you lose some grading information. But I would strongly suspect that there is a similar story for SLN. But it hasn't been worked out so far.
You stated your pairing theorem for the Barnatan invariant and the Khovanov invariant. If you do Barnatan invariant and Barnatan invariant, do you recover the Barnatan homology?
Yes.
And then why do you not have a Conway mutation theorem for Barnatan homology?
Yeah, that's a good question. And they're all good questions. I don't think the proof that I just presented is a book proof. I think that we're still missing something. And I would say that Barnatan homology should also be mutation invariant in that sense, Conway component preserving. So it's really our proof depends on this geography result. And it's somehow not clear how you get restrictions on the curves, how you count the number of Ds that appear in the components of the Barnatan invariant. So they can look much more complicated than this. So this classification result is just nowhere near true for the Barnatan invariant. So those curves can look complicated. They can be nonlinear. They can carry non-trivial higher local systems. So I have one example with a two-dimensional non-trivial local system. They can look fairly wild. The one thing that we know is that they can't they can't wrap around the special tangle end, but it can wrap around other tangle ends, and so that makes it harder to count the number of Ds. That's mainly the issue here.
Do you have any sense of what happens to the spectral sequence to, say, the blur homology of the double cover?
That's a good question that Liam could tell you maybe more about this. He has thought more about this than I. There should be a local version of this. But it's not been worked out.
Okay. Unless there are any more questions, let's thank Claudius again. All right, and I have a few announcements. So if you are offered funding for travel, you should check your email over the next week. You'll get an email at some point about how to get reimbursed. If you ask Vera to print a poster for you and haven't paid yet for it, please come up here to meet with Vera at the end. And also, if you're still here and you were a speaker or an organizer, if you could come up to the front after the talk. And I think that's it, right? Okay. All right. Thank you, everyone. It's been great having you all here.